Hey everybody, and welcome to another episode of Data Science Foundations. We left last episode on a cliffhanger. We were wondering whether we could learn. So, as data scientists, as machine learners, we're seeing data and we are trying to approximate. We're trying to figure out what the function was that generated the data, right? And we wanted to know whether we could actually learn. And we showed yesterday that it didn't seem like we could. We got some data points, and if we've seen these points before, so if we've seen a particular loan application before, we can have a good guess as to what the answer should be. But if we've never seen a particular loan application before, so it's new in some facet, it's a new type of job, or the salary is slightly different, then we have no idea. The problem that we sort of stumbled across, the thing that we talked about right at the end of class, was the same problem that we talked about previously when we were talking about how do we infer things about data that we have not seen. Do you remember how we did that? Well, if you don't, we'll revisit it this time. So I'm going to make a tangent. This will sound like it's completely different, but it's going to be very similar. So I'm going to start off by talking about a bin. So imagine I've got a bin or a barrel, and it's filled with balls, and the balls are either red or they're green, and there's infinite number of balls in there. So there's infinite number, but there's a ratio of red balls to green balls, right? So there's infinitely more red balls than green balls, or something like that. So I've gone ahead and I've specified a function that would sort of simulate this. So I've made a quote-unquote secret probability. I sort of hid what the probability would be by writing in a binary number. So anyways, if you guys know binary, then you might know what this number is. But if you don't, then you get to sort of be like, ooh, it's secret. So anyways, we've got this bin. I can go ahead and I can sample from this bin multiple times to go ahead and get a sample with multiple balls. So in this case, we get back a sample. There's lots of red. There's a couple of green. Okay. So first question, is this bin a random variable? And your gut might say, yeah, it definitely looks like a random variable. But remember, the one thing that we need to have for it to be a random variable is that it needs to return a number. So it's a function that returns a random number. So it doesn't return a number, so it's not quite, but we could easily convert it to a random variable by transferring the greens into a 1, maybe the reds into a 0, or something like that. Second question I ask you, what do you know about this bin? Do you have a feeling as for what the probability would be of drawing a green ball from the bin versus a red ball? And the honest truth is you'll probably know two things. So based on this sample, you certainly know that the probability is not 0 to draw a green ball. And it's not 0 to draw a red ball, but you really have no idea for certain. This sample could be misrepresentative. Perhaps there's only like 10 red balls in the entire bin, and there's a bajillion green balls in the bin. For some reason we drew this sample that looks like this. So we're in the same situation. We have some data that we've seen, and we want to infer things about lots of data that we haven't seen. How would we do this? Well, if you remember before, we needed one more assumption. And what was that assumption? Well, that assumption was that these samples were independently and identically distributed, and that they were drawn from a random variable. So they're from a probability distribution. And what can we do when we have this assumption? We can do so much. If you remember, when we had this assumption, we could do the entire Bootstrap confidence interval performance that we did previously. Okay, so let's do this. So let's say we're very interested to figure out what the probability of getting a green ball was from this bin. So in our case, we would go ahead and do Bootstrap. So the first thing that we would do is convert this into a number. So in this case, greens are 1s and the reds are 0s. I go ahead and I do bootstrapping to go ahead and get in this case, this is a sampling distribution of not the sample mean in this case, but of the probability that we would draw reds or greens from the bin. So we see that the probability is somewhere maybe around 0.25, which is what it was. But we can obviously tell the probability is going to be more than 0, and it's going to be It's going to be probably less than 0.5, most certainly, based on just this distribution itself. We don't need to go ahead and construct the full confidence interval here. Okay, that's interesting. And you're like, well, Nate, that was very interesting. Thank you for taking me on this detour about bins and balls. But what gives? We were talking about machine learning. That's like the whole point of data science, right? Well, let me sort of bring the connection to you. So remember, we ended last class with the question, was it possible to learn? Well, surprise, the bin example told us exactly it was. So let's make connections. So assume that each ball in the bin is a data point. There are infinitely many. And now assume that we have a hypothesis. So we've thought very hard, particularly about loan applications, and we've decided to only accept people above a specific FICO score, and only if they have an income above this level, right? So we've made a function. This is our hypothesis function. Is it the true function? Likely not. Likely there is a better function that takes in more things about this person. Perhaps their spending habits, perhaps how much they exercise even, or something like that. So we've got a hypothesis, and let's say, just for hypothetically speaking, we took this hypothesis and we applied it to every single data point imaginable. So we applied it to every single person in the entire world, and in the future world, and in the past world. And we figured out how many times, or we figured out whether for each person our hypothesis was going to be right or wrong. Okay. So in this case, there would be a lot of times where it would be wrong, and maybe sometimes where it would be right. Okay. So remember, each ball was a data point in our example. I'm going to say that each green ball in our ball bin example was a situation where our reported hypothesis, the one that we thought really hard about and came up with, would be correct. Each red ball was one where it would be incorrect. You probably see where I'm going. So now, because we've already learned that we can say, well, based on the Bootstrap estimate, the probability of getting a green ball is 0.25 based on this example. If the balls were data points and their color was correct or not, we can actually predict how well our final hypothesis, our prediction, will do on the data set at large. How? We get a sample. We see how well it does on the sample. We do a Bootstrap confidence interval, and we get the accuracy for the entire population. So again, we extrapolate from a sample into the entire population. Okay, pretty cool. You're again like, okay, I'll admit that's pretty cool. I didn't really know how we were going to get past this idea of not being able to learn. But the important thing here is that we know that the data comes to us in a very specific way. It comes to us from a specific probability distribution where we're getting independent draws from it. If we don't get that, this means we could get a sample initially that we're training on, or we could get a sample that we're testing on that is vastly different from the majority of the population. And if we get a sample that's vastly different from the majority of the population, then we can't actually say anything about the population. One of the ways, and this is not the only way, but one of the ways that you can ensure our sample is similar to the population is by getting random draws, aka independent identically distributed draws. So why does this matter? Well, this matters because we can learn. Wow. Okay, so we can do machine learning now. Well, why haven't we solved everything yet? Well, we'll get into that. There are some more problems that we'll discover. The next class, I wanted to go ahead and I'll present a cautionary tale. And this is the idea of testing multiple hypotheses against the same test set. So we've learned that we can learn. Let's refine our knowledge on how we can learn. So the specific way we've learned that we can learn is we can think very hard, find a hypothesis after thinking very hard, and write our hypothesis down. We get a sample from the true population. We need to make sure the sample is random. And then we try our hypothesis on each individual in the sample. And then based on this tried hypothesis on each individual in the sample, the accuracy or inaccuracy of each, we can do a Bootstrap estimate for the entire population to see how well they'll do. Okay. So I do want to just go ahead and let you guys know there are other approaches to sort of getting to this result. The way I've done it is probably the least formal. I kind of like it because it relies on the bootstrapping stuff that we had done in the past. The normal way people do this is something called the Hofting inequality, but we're not going to go over that. It's super complex and probability speak, but I'll go ahead and I'll include a link in the video description below. So if you're interested in it, just sort of click on the link and you can sort of get a much more mathy approach to what we've done here. Okay, so we learned that we can learn, and we learned that we can learn by means of doing the exact same bootstrap confidence interval as we did before, by inferring things from the sample that we know to things to the population that we've never seen before. Okay, well, I'm really excited that you guys joined me for this. This was kind of hopefully a little bit interesting for you guys. I went ahead and I put some comprehension questions down below. If you are interested, please go ahead and sort of write down your own answers to the comprehension questions. Don't look at the comments. And then once you're done, go ahead and look at the comments. And if someone has already answered something similar to you and I've responded to them, just go ahead and be like, yeah, I got it right. Or like, oh, interesting, I didn't think of that. But if you have a novel answer or something like that you wanted to get my response to, go ahead and comment it. If you're the first person here, just comment the responses. I'll go ahead and I'll let you know if they're right or wrong. Okay, thanks, and join me next time while we talk about better ways to learn.